Alrighty, good morning, lads and ladies. I appreciate your patience. My wife had to leave early for work this morning, so I had to take care of all the animals and stuff. But yeah, thank you. Thank you for your patience. I don't want to waste any more of your time, so I'm gonna flip on the dot cam. We can get started right away. Alrighty. Come on. Come on now. There we go. All right. I did see one or two things in the Discord that I wanted to address a little bit. Don't switch. So I haven't had time to go back and review. I heard a few things popping in last night. I just wanted to comment that this image, this line right here, this is good. You can stop here. The only tiny error in this, we would want to close a parentheses at the end of this 2i over n, which is under the square root, but this looks beautiful. This looks perfect. And I saw that there was a little bit of uncertainty about how far we need to go there. I can come back in and address those in greater detail a little bit later, but yeah, very good work there. These take some time, they really do. And learning to master that notation, that capital sigma notation, is a no bullshit big deal. The good news from the perspective of this class is that after next Monday, you will be freed from sigma notation. You will no longer need to use it for the remainder of this class. However, a good chunk of Calc 2, approximately a third of Calc 2, will have you working again in that sigma notation with infinite series and also with power series. So taking the time now to master it will not only help you understand integrals on a deeper level, but will also be hugely helpful when you get to the infinite sequences and series portion of Calc 2, which is precisely the part of Calc 2 that gives it the reputation it has. So enough chit chat. Today is the 26th of March, 2021, I believe. And today we're going to talk about anti-derivatives, which, believe it or not, is section 4.9. So we're going a little bit out of order here, but believe me, it's the right thing to do. It turns out that the area problems that you've been solving in this sigma notation and graduating to working with the integral notation, that problem is dramatically simplified by this concept of an antiderivative, together with the help of a very special theorem called the fundamental theorem of calculus. And that theorem is every bit as important as it sounds. You hear the word fundamental, you go, oh shit. You hear the word theorem, you go, oh fuck. And then of calculus. So you kind of get the feeling that it's a big deal relating to all things calculus, and it is. But before we can talk about FTC, the fundamental theorem of calculus, which will be the thing that liberates you from the hell of sigma notation, we need to learn about antiderivatives because they're one of the primary objects therein. So let's do it. As with all things mathematical, we must begin with a definition. An antiderivative for the function, I will use little f of x, is another function for which I will use big F of x, satisfying big F primed of x is equal to little f of x. So it is what it sounds like. I'm hyphenating antiderivative here just to help you see the, what's the word, etymology of it, right? It is the undoing of a derivative, but often it's given as one word with no hyphenate. So the idea is, if I give you some function little f, can you find another function big F whose derivative is little f, right? Can you go backwards in the differentiation chain? We know how to go forwards in the differentiation chain. We know how to differentiate once, twice, 3 times, 4 times, however many times. We know how to take derivatives, but do we know how to untake derivatives? This is the question. The answer is, generally speaking, but in certain special cases, yeah. Antiderivatives turn out to be much, much harder than regular derivatives. But there are a handful of special cases. Many of them are the nice ones, like trig functions, polynomial functions, that sort of thing, where there are good, simple rules for finding an antiderivative. A quick note. If capital F of x is an antiderivative for little f of x, then so is capital F of x plus c for any constant c. This is because ddx of capital F of x plus c is equal to ddx of capital F of x plus ddx of c. All right, the derivative is a linear operator, meaning split up over addition. The first piece here is capital F primed, right? ddx of something is the derivative of that thing. So this is going to be capital F primed of x. And the derivative of c is 0, right? Because c is a constant. Differentiate a constant, you get 0. And capital F primed here is by definition little f, because capital F is an antiderivative for little f, which means that capital F primed is little f. So this is little f. So not only if you have one antiderivative, you can get another by adding a constant, right? So if x cubed is your antiderivative, then x cubed plus 2, x cubed minus 7, x cubed plus pi, all of those would also be antiderivatives. This leads to a concept. We say the most general antiderivative of little f of x is big F of x plus c, where big F of x is a particular or known antiderivative and c is what's called an arbitrary constant. So we use this word arbitrary to say, okay, I don't know what c is. I don't have any particular concern about what c is. But oftentimes we're interested in finding the most general antiderivative. That is like the class of all functions whose derivative is little f. And once you've found one of them, once you find a particular antiderivative, you find any function who differentiates to little f. If you want to describe all the functions that differentiate to little f, you just slap on a plus c. It is a fact that if you have two antiderivatives, they must, for a particular function, they must differ by a constant. So it really is the case that once you find a single antiderivative, if you slap on a plus c, you genuinely do have all of them. It's a consequence of the mean value theorem, actually consequence of Rolle's theorem, which we'll discuss a little bit later in the context of integrals. All right. Let's look at a few concrete examples before we go any deeper into theory land. Any questions on the definition here, or what we mean by most general antiderivative? Okay. I think it's wise to start off without any rules. Start off just trying to think about some shit, and then we'll deduce some rules, and towards the end, we will compile those rules into a table. But I'd like you guys to just think along with me, because this is the sort of thing that you can do without too much guidance, I think. So let's find an antiderivative for little f of x equals 2x. And I want you to think for just a second. So I'm trying to find a function whose derivative is 2x. I don't want to differentiate this.
Would it be x squared plus c, but
Yeah, that's it. Adrian nailed it. So we're trying to find somebody who differentiates to 2x, somebody whose derivative is 2x. And we've seen this show up so many times in our past calculations that just from memory, we know that the derivative d dx of x squared is 2x. So here, capital F of x would be x squared. This guy is an antiderivative. For little f, x equals 2x. And what's more, the most general antiderivative and I think Adrian got this as well, antiderivative is x squared plus c. And c could be any constant, right? If you differentiate any function that looks like x squared plus a constant, you'll get 2x. Because capital F primed here would be d dx of x squared plus c, which is 2x plus 0, which is 2x, which is little f. So your particular antiderivative, if you just needed to find one of them, x squared is sort of the most natural. You could say x squared plus 1 if you wanted, but you could also say x squared plus 10 or x squared minus 5 or x squared plus pi, and we encapsulate that in this. And the good news with antiderivatives is you can always check your work. If you're not sure if you found the right antiderivative, differentiate it. You should get the original function, right? That's the whole game. So this will also provide you an opportunity to kind of resharpen your differentiation skills by checking your work. If you're confident the antiderivative is correct, but then when you differentiate it, you get something else, maybe you need to sharpen that differentiation skill, or maybe your antiderivative isn't correct. But if you're confident the antiderivative is correct, then you need to check the differentiation. Okay, let's try one more. This time I'm going to say find the most general antiderivative, because that's what we ended up doing here anyway. Find the most general most general antiderivative of little f of x equals 2 cosine x. So who can we differentiate to get 2 cosine x?
Wouldn't it be like sine x squared?
Well, if we wanted to differentiate sine, like sine squared of x or the sine of x squared, both of those would require the chain rule. So I think you're thinking a little bit too hard, Mackenzie, but you're on the right track. We're going to need a sine, right? Because the derivative of sine is cosine.
It'd be 2 sine x.
But yeah, exactly. Just 2 sine of x, because 2's the constant multiple out front, remember, just comes along for the ride. So this guy is not the result of a power coming down. He's just chilling. So here we know.
Is there something that like shows that that's not a power coming down, or well, we just kind of have to like figure that it's a constant?
Well, yeah, so if this was a power coming down, then by the chain rule, we would have another piece over here, right? Imagine I differentiate sine squared of x, I would get 2 cos x, but then by the chain rule, I would get a sine x at the end as well, right? So kind of it's about thinking of the differentiation rules. The particular differentiation rule that tells me that this 2 is just a multiple coming along for the ride is that when you take derivatives of constant multiples, they really do just come along for the ride, right? Remember that a number multiplying a function, when you differentiate it, just comes along. It pops out past the derivative.
Thank you.
Is that ringing a bell? Yeah, exactly. And then you could also, of course, check if we thought maybe sine squared x was the guy, you could certainly check by differentiating sine squared x, and you would get 2 sine x cos x by the chain rule. Okay, so capital F here would be 2 times the sine of x plus a constant. All right. I think before we go any deeper, there's a few theorems in the textbook that I'd like to give a quick nod to. So let me pop this up. Section with you. So the definition of an antiderivative, and then most general antiderivative. We can talk about natural log stuff, power rule stuff. Oh, no, they're not. They shove the theorems later. Okay, that's fine. We can go ahead and start breaking down the rules then. We'll do this last example here. Okay, so I'd like to find an antiderivative for the function 1 over x, assuming that x is positive. And I want you to think about the assumption for a minute. Why that's important. So who do we know that differentiates to give 1 over x? Whose derivative is 1 over
x? Sorry, x to negative 1.
So this is x to the negative 1. Yep. But I'm trying to find somebody that differentiates to this. And I think thinking of it as x to the negative 1 makes us think power rule. We actually need to step away from that. In every other instance, Adrian, every other instance where you have a power function, you would think of it that way. But this is the one exception. And I think there's a meaningful hint in this. There's a reason why we need this assumption.
Is it ln x?
Yeah, think about the curve sketching problem from exam 2. The derivative of the natural log of x is 1 over x. So I would say we know that d dx of the natural log of x is 1 over x. So here, capital F would be the natural log of x. And if we want the most general antiderivative, we would say plus c. So why the x greater than 0 assumption? What does this have to do with this shit?
Because if x is negative, it's undefined.
Very good. The natural log function is only defined on the positive numbers, right? The ln of -1, for example, does not exist. The ln of 0 does not exist. Now, this does get more subtle. If we're allowed to assume that x is positive, then the antiderivative really is just natural log of x plus a constant. But I want you to think along with me for a second about the chain rule. I want to look just a tiny bit deeper at this natural log business. Let's think a little bit more about antiderivatives for the function little f of x equals 1 over x. If, due to the problem, whatever, it's a physics problem, real world problem, where you're allowed to assume that the variable is positive, then saying the antiderivative of 1 over x is the natural log of x is totally fine. But in mathematics, we like to pursue generality, right? We want an answer that always works, no matter what assumptions are baked into the problem or not. To this end, what's the derivative d dx of the natural log of -x? And I know at a glance this looks off-putting, but remember, if x is negative, then -x is going to be positive, right? So this function, while it might look like it's never defined, it actually is. This function is perfectly happy, but it just requires x to be negative instead. So in other words, I'm trying to come up with an antiderivative where I flip that assumption around. Instead of saying assume x is positive, let's assume x is negative. If x is negative, then the natural log of -x is fine, right? Plug -2 in here. You get the natural log of -2, which is the natural log of 2, which is totally fine. But symbolically, just computing derivatives using the chain rule without thinking too hard about any of the domain stuff, how would I take this derivative?
1 over -x.
Good. And then
Times -1.
good, right? By the chain rule, we need to multiply by the derivative of the inside. And the derivative of -x is -1. So this would be 1 over -x times -1, which is -1 over -x, which is 1 over x again. Isn't that a little bit funky? So there's really two antiderivatives for 1 over x. Yeah? The derivative of the natural log of -x is 1 over x, and the derivative of the natural log of x is 1 over x. So how can I roll these two facts into a single statement? So really, the most general antiderivative of f of x equals 1 over x is capital F of x equals natural log of negative x if x is negative. I'll write it like this. ln of negative x if x is negative, and the ln of positive x if x is positive. And I should say, plus c. Forgive the notation here. There's a much nicer way to write this. Nobody would write it like that. What we write instead is the natural log of the absolute value of x. Because negative x if x is negative, positive x if x is positive, that is the absolute value function. So this is the result that we want to discover for 1 over x. It turns out that this works great whether x is positive or negative, right? If x is positive, then you're just looking at regular natural log of x, whose regular derivative is regular 1 over x. If x is negative, then the absolute value of x is negative x. And as we just discovered, the derivative of the natural log of negative x is also 1 over x. So this captures both of those. Cool stuff, right? So in practice, here's some things we need to remember. I will put these into, well, let us also discover the other one before I put it into a table. Questions on what we've done so far, and anything that we need to go back to or want to look at a little bit more closely before I start moving. All right. So we've seen how to find antiderivatives for just a few functions, right? 1 over x, 2x, and 2 cos x. It turns out that these sort of antiderivative rules can be generalized. So if little f is 1 over x, we saw that big F, and I'm not going to write the plus c's here, is the natural log of the absolute value of x. Seeing that this guy, 2x, has antiderivative x squared, and this guy, 2 cos x, has antiderivative 2 sine x. Item 2 can be generalized significantly. What's really going on with item 2 here? Well, it's that I recognize this as the output from the power rule for this. So we'll say recall the power rule for derivatives says that d dx of x to the n is n x to the n minus 1. This is the thing that everybody remembers from the first half of the course. Seems like everybody retains this one. So if we have the ability to kind of run that backwards from 2x to x squared, we should be able to run that backwards for anything like this. And indeed we can. When you differentiate a power function, this is true, by the way, for all n. Are there any exceptions here? Yeah, for all n, right? If we try to run this backwards, let's think about it. To differentiate a power function, you bring that power down and reduce the power by 1, right? So the derivative of x cubed is some number times x squared. The derivative of x to the 5 is some number times x to the 4. The derivative of x to the n in general is some number, in particular n, times x to the n minus 1. So if you want to antiderive x to the n, if you take a regular derivative, the power goes down. So if you take an antiderivative, the power goes up. Right? We want somebody whose derivative is just plain old x to the n. Well, it's going to have to be something times x to the n plus 1, right? Because when you differentiate x to the n plus 1, you know that this power is going to go down by 1 and become x to the n. But that's not the only thing that happens. If you were to differentiate x to the n plus 1, you would get n plus 1 times x to the n. And in order to get rid of that n plus 1, we need this. The proof is right there. We just said it, but let's prove it. If capital F of x is 1 over n plus 1 times x to the n plus 1, then capital F primed of x is d dx of 1 over n plus 1 times x to the n plus 1. The crucial thing to recognize here is that the derivative is being taken with respect to x. So 1 over n plus 1 is a constant, right? It's like 2. It's just a constant. So it's going to come out. And then we just have d dx of x to the n plus 1. But what is d dx of x to the n plus 1? By the regular power rule for derivatives, I'm going to reduce this power by 1 and pull the old power down. This 1 over n plus 1 is just coming along for the ride. It's a constant multiple. And then the derivative of x to the n plus 1 is n plus 1 times x to the n. And these cancel. So we get just good old-fashioned x to the n, and that's the proof. So this is your power rule for antiderivatives. And we could play this game with lots of other functions. In fact, if you take the table of known derivatives I'll hold here just for a second. If you take the table of known derivatives from the end of chapter 3, the thing I said you need to be comfortable with moving into exam 1, you take all of those, then you just read them backwards and you get antiderivatives. And I want to sort of just give you the list of antiderivatives you must know. Any questions on the proof here? I think perhaps the only tricky part is recognizing that this n+1 needs to be in parentheses. Is everybody comfy with why that's the case? Because it's multiplying everything there. It is a single chunk. It is just whatever number comes down from the power. So it really is a single chunk. In the language of linear operators, what we're doing is defining the inverse for the ddx operator. And you may notice that here, right? It would be nice if I could like take an inverse of this thing on both sides. Imagine this was a matrix. I know everybody loved matrices in pre-calc, right? But if I wanted to apply the inverse matrix to both sides, then over here I would get x to the n, and over here I would get whatever the inverse matrix does to this. Turns out to be this. And in the vector space of differentiable functions, it really is described that way. So if the concept of linear operators is fascinating to you, if you have any sort of taste for matrices back in pre-calculus, then this is sort of the next step up from that, is thinking about inverting generalized linear operators. And that means you have a future in quantum physics, my friend. So let me go ahead and describe for you now all of the antiderivatives that I am expecting you can. Need some more paper. You can find this table in the textbook in two places. Over here, I will put little f of x, and over here, I will put capital F of x. And I'm not going to be writing the plus c's. And I'm not going to be writing the algebraic rules that describe the antiderivative as an operator. I'm just going to be writing the specific functions I need you to know. X to the n. His antiderivative is 1 over n plus 1 times x to the n plus 1. This is what we just proved. This works for all n except -1, because x to the -1 is 1 over x. So whether you see it written like this or you see it written like this, we know that his antiderivative should be the natural log of the absolute value of x. An antiderivative for cos x, who differentiates to become cosine, well, that's sine. And while we're there, we should talk about sine x. Who has the derivative sine x? Well, it's not cos x, right? The derivative of cos x is negative sine x. So the antiderivative for sine x has to be negative cos x. And we might think that, cosine and sine, the next are going to be like secant and tangent. But those antiderivatives turn out to be a little bit gnarlier. There are some that we can talk about nicely, though. Secant squared x, whose derivative is secant squared x.
Tangent x.
Excellent. So we really are just reading our derivative table backwards. I can't readily talk about an antiderivative for tangent. We need some tools that are a bit beyond what we have now to do that. We will learn them later. But another one that we can talk about right now is secant x, tangent x, whose derivative is secant tangent.
Secant.
Good, secant. And there are co-function derivatives that match these, like whose derivative is cosecant squared.
Cotangent.
It's almost cotangent. We're on the right track.
Negative cotangent.
Very good, negative cotangent. Remember, the derivative of cotangent is negative cosecant squared. So the antiderivative for negative cosecant squared would be cotangent. So the antiderivative for cosecant squared would be negative cotangent x. And similarly, if we talk about cosecant x, cotangent x, this guy's antiderivative is negative cosecant x. And that gets the power functions and trig functions out of the way. Here's everybody's favorite one. What's an antiderivative for e to the x?
E to the x.
Yeah.
Very good. Yeah, e to the x. All right, here's a few trickier ones. What is an antiderivative for 1 over 1 plus x squared? Don't think too hard. You don't have to apply any of these other rules or try to split this up. It's just something we should know. Who has this as its derivative?
Wouldn't that be inverse?
Inverse tangent.
Excellent. Arctan or inverse tangent of x. Good. And 1 over the square root of 1 minus x squared?
Arcsecant. Arcsine.
Very good. Arcsine or the inverse sine of x. All right. I think I will stop here. There are others we could list. All right. The inverse cosine function, his derivative is the negative of this. So if you put a negative here, this would be inverse cosine. We also learned the derivatives for inverse secant, so we could write him in this antiderivative table. But these are the basic ones. These are the ones that I really want you guys to know. The complete table can be found in section 4.9, but these are the ones that I require you to know, i.e. these are the ones you'll be tested on. Something missing here. I don't think so. We didn't talk about hyperbolic functions. Oh, all right. Really quickly, I want to show you this table. You've got the general base exponential. I won't beat you to death with that, although we should talk about it. Is that all they give us there? They're not giving us anything else. Okay, I guess they wait for 5.2 for the others. While we're here talking about e to the x, it is worth mentioning this is a special case of little f equals b to the x and big F equals b to the x over the natural log of b. This is a consequence of the regular differentiation formula. Again, the regular derivative of b to the x for any base b other than e is b to the x times the natural log of b. This one doesn't get used a whole lot, but it does show up sometimes. It's kind of in between stuff I would omit from this list as being like not quite worth shoving in your memory, and stuff that is definitely worth being on this list, which is all of these things. I would not forget this, even though you're not going to use it a whole lot. This is something that does tend to show up, especially in the early parts of Calc 2. All right. So these are the main things. These are the principal building blocks for our antiderivatives. And just like there is a product rule for derivatives, there's a kind of anti-product rule for antiderivatives. Just like there's a chain rule for derivatives, there's a kind of anti-chain rule for antiderivatives. All of those things exist. And we will get to talking about them in time. But for now, I want to give you sort of the fundamental rules for antiderivatives. You can kind of think of these as the building blocks and the fundamental rules as the glue or the mason, the cement that we'll put them together with. Namely, the antiderivative obeys the same sort of rules that regular derivatives obey. So constant multiples pop out. You can split up over addition and subtraction. So from this table and these rules, we can cook up many, many, many antiderivatives. At the outset here, we will understand that capital F primed of x is little f of x. So capital F is an antiderivative for little f. And capital G primed of x is little g of x. And I know it's bad grammar, I'm sorry. And k is a constant. Then an antiderivative for k times little f of x is k times big F of x. Because if you differentiate this, the constant just pops out and you get k times big F primed, which is k times little f. Also, little f plus little g will have antiderivative big F plus big G. And this is that familiar set of rules, right? We saw it with the derivative, we saw it with the sum, we saw it with the integral. These two things together are called linearity. The antiderivative is also a linear operator. Okay, so coming back here, I want to note one particular thing. This works even when n is 0. Not something that people always realize right away. This works for all n except -1. That includes n equals 0, which means the derivative of a constant, x to the 0, would be that constant times x. It's not immediately clear, so you might want to think of that as an extension. This includes the fact that some, we'll call it k, constant, will have antiderivative kx. I wouldn't normally think of this as a separate thing, but I think sometimes folks don't realize that that is actually included in this case. So it's worth saying. The antiderivative of a constant is that constant times x, right? Because the derivative of kx is just k. Okay, with this out of the way, let's talk about some slightly more complicated problems. The main thing we use is linearity and algebra. So if I give you some complicated function and I ask you for an antiderivative, your job is to split it up into little simple pieces and then apply the table to each of those little pieces. We'll take an example from the text. Let's start with this guy, 4 sine x plus 2x to the 5 minus root x over x. So we'll say find the most general antiderivative for g of x equals 4 sine x plus, what is it, root x minus x over x? Oh no, 2x to the 5 minus root x over x. And at a glance, this looks pretty intimidating. 4 sine x, I know how to handle that. That's not going to be too bad. But this piece looks quite intimidating. It doesn't look anything like the stuff from my table. The trick is, as I said a second ago, use algebra rules to split this up into little pieces, each of which we know how to handle. The trick here is, again, just simple algebra, right? A minus b over c is a over c minus b over c. You can split up the fraction. It's 2x to the 5 over x minus the square root of x over x. And then each of these, this and this, will simplify to a power function. So we'll have, a trig function times a constant plus a power function times a constant minus a power function, each of which we know how to handle. And according to the rules above, we are allowed to handle each of those separately. Two times x to the 5 over x is 2x to the 4 minus the square root of x is x to the 1/2. X to the 1/2 divided by x is x to the negative 1/2. The algebra rule at play there is x to the a over x to the b is equal to x to the a minus b. So this is x to the 1/2 over x to the 1. That should be x to the 1/2 minus 1. And 1/2 minus 1 is negative 1/2. So now I'm ready to find my antiderivative. Capital G. Capital G is the antiderivative for little g, which should be the antiderivative of this thing. So to each of these little pieces, I will apply the rule from the table. The constant multiples are allowed to come along for the ride. So we don't have to worry about the 4. The 4 is just coming along for the ride. We don't have to worry about the 2. The 2 is just coming along for the ride. And the addition rule here tells me I'm allowed to split this up. And as always, what works for addition here? If it works for addition and constant multiplication, it works for subtraction also. All right. An antiderivative for sine is what? The 4 is going to come along for the ride. What's an antiderivative for sine x?
Negative cosine.
Very good. Negative cos x. And remember to write your variables in here. Then we'll have plus 2 times an antiderivative for x to the 4. What is an antiderivative for x to the 4 going to look like according to my power rule? Well, remember what our power rule for antiderivative says. It says we should have 1 over n plus 1. That's 1 over 4 plus 1 times x to the n plus 1. That's x to the 4 plus 1. And that same rule we will apply here. So I'll have minus, and now I'll have 1 over negative 1/2 plus 1 times x to the negative 1/2 plus 1. All right, so each of these pieces, x to the 4 and x to the negative 1/2, can be handled with our power rule. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And this piece is just one of our straight up trig antiderivatives. Oh, we can simplify this. This is negative 4 cos x plus 2 times 1 over 4 plus 1 is 1/5. So this is 2 times 1/5 x to the 5 minus negative 1/2 plus 1 is positive 1/2. So I'll write this as 1 over 1/2. And I should put the bottom in parens like that. And if we want to, we can leave the big parens around the outside, but we don't need them. And then x here is being raised to that same thing, negative 1/2 plus 1, which is positive 1/2. I suppose I should be writing my plus c's at the end, I'm sorry, because we want the most general antiderivative. And we can clean these up a little bit more. That's negative 4 cos x plus 2/5 x to the 5 minus 2 x to the 1/2 plus a constant. If you gave me this on a test, it would be fine, but I wouldn't want it as this. I would want you to simplify at least to this point. I want to know, what are these powers? What is this fraction? What is this power? What is this fraction? Questions on this guy?
Did you get the 2 at the end, where you just like flip that fraction, kind of?
Yep, exactly. If you divide 1 by 1/2, that's the same as multiplying 1 by 2 over 1.
Okay.
Other questions on this guy? Okay, let's try 1 or 2 more. So here they're talking about something called a differential equation. It's a particular kind of differential equation called an initial value problem. Let me introduce this a little bit. So we've seen that the most general antiderivative for a function little f is big F of x plus c, where c is an arbitrary constant and big F primed is little f. What kind of animal is this? My first thought would be that it's a function, right? And f of x is a function, so f of x plus c should just be a function. But the fact that c is an arbitrary constant means that this isn't just one function. It's an infinite family of functions. What these functions all have in common is that they have the same derivative. If you differentiate any function looking like this, f of x plus 1, f of x minus 5, whatever, they will all have the same derivative, which means they all have the same slope. Let me show you what I mean. Antiderivative for x squared would be x cubed over 3. But not just that, that plus 1, that plus 2, that plus 3, that plus 4, that plus 5, that minus 1, that minus 2, that minus 3, that minus 4, that minus 5. And what you notice is that if you pick a particular x value, let me look at the line x equals -1, and look at the slope of your function, your antiderivatives at any one of those points, the slopes all match, right? If I look right here, or right here, or right here, or right here, or right here, all of these functions have the same slope at x equals 1, -1. They all have the same slope at x equals 0. They all have the same slope at any particular x value. If I were to look at x equals any particular value, all of these multicolored functions here have the same slope at any particular x value. So the most general antiderivative for a function is this family, this infinite family of vertical translates. It's all the vertical translates of a given function because they'll all have the same slope at any given point. That's what this means. Sometimes instead of the most general antiderivative, we want a particular antiderivative. Satisfying some what are called initial conditions. Initial conditions, this is like I tell you what f prime of 0 is. I tell you, okay, I need capital F primed of 0 to be 2. Or something like that. Or sorry, I need capital, forget the prime, capital F of 0 to be 2, or something like that. Yeah, please erase or scratch out the prime there. These sort of problems are called initial value problems. So I give you the derivative I give you little f, and I ask you to find big F. But then I don't just want any big F, and I don't want big F plus C. I want one of these guys, meaning one of these guys. So if I add to this requirement, if I add to the problem, find an antiderivative for x squared. Any one of these would be an antiderivative for x squared. But if I say find an antiderivative for x squared that's equal to 2 at 0, that picks this guy out. That says, no, I don't want any of those. I don't want any of those. I just want this guy. Right? This is the only one of those that satisfied f of 0 equals 2. So what these initial conditions do is they allow us to pick from this whole infinite family of things a particular one that is equal to 2 when x is 0. Now, it doesn't have to be f of 0 is 2. It could be anything. But I give you some particular set of initial conditions, and that will allow you to solve for the constant c. It will allow you to pick one out of this infinite family of functions. These are called initial value problems. And they're hugely important in mathematics and in physics, especially in kinematics, rectilinear motion. You remember the velocity problems we've been talking about, right? All of those things. Every time we talked about, position, velocity, acceleration, whether we're talking about areas or slopes or whatever, any problem of that nature where you end up taking an antiderivative and then need to pick a particular antiderivative based on some initial conditions, those are called initial value problems, and they're especially dominant in physics. I'd like to show you an example of an initial value problem here. We're going to take a look at this one. So it says find f if f primed is e to the x plus 20 times quantity 1 plus x squared to the negative 1 under the assumption f of 0 is negative 2. We're going to run just a tiny bit over time here. I'll ask you to please be patient since we were just a few minutes late getting started. Find f of x given f primed of x is equal to e to the x plus 20 times 1 plus x squared to the negative 1. And what did we say? F of 0 is negative 2. So they gave me f primed and they want me to find f. That means I need to undo this derivative. I need to take an antiderivative. So I need to start by finding an antiderivative for this function. That antiderivative will involve a plus c. Then, in order to solve for that plus c, find a particular antiderivative, I will plug in these initial conditions and solve for c. Here's how this looks. F primed of x, I'm just going to rewrite this a little bit differently. This is e to the x plus 20 times, what is 1 plus x squared quantity to the negative 1? Well, it's the reciprocal of 1 plus x squared. They're just trying to disguise it so you don't recognize it. They're trying to scare you. We know an antiderivative for e to the x, that's on our table. This is a constant multiple, so he's just going to come along for the ride. And we know an antiderivative for 1 over 1 plus x squared. Since they didn't give us little f and ask for capital F, they gave us little f prime and asked for little f. It's the same thing though, right? You need to undo this derivative. So the antiderivative for little f primed is just little f. And he will be equal to e to the x, because the antiderivative of e to the x is e to the x, plus 20 times the antiderivative for 1 over 1 plus x squared. We talked about that a second ago. That's the inverse tangent of x plus a constant. Is everybody with me on this so far? That to get little f from little f primed, you do the same thing to go from little f to big F. Right? This is an antiderivative for this. Questions about just that conceptually? Any issues there? Any curiosities? Okay, and then on the technical point, are we all comfortable with why this becomes this and this becomes this? An antiderivative for e to the x is, look at the table, e to the x. An antiderivative for 1 over 1 plus x squared is, look at the table, inverse tangent of x. And the 20 here, being a constant multiple, comes along for the ride, stays a constant multiple. You could check by differentiating that the derivative of this is indeed this. But I'm not done. Because they've specified some initial conditions, I need to solve for c. This is an infinite family of functions. They just want one of them. They want the one particular function that satisfies this. Think about the picture over here in Desmos again. They don't want all these things. They just want one of them. They want the one that satisfies f of 0 is equal to, in this case, -2. So how do we do that? Well, if f of 0 is -2, that means when I plug 0 in here, this whole thing needs to be equal to -2. Now, f of 0 is e to the 0 plus 20 times the inverse tangent of 0 plus c. F of 0 is supposed to be -2. E to the 0 is 1 plus 20 times, what is the inverse tangent of 0? I know this inverse trig stuff catches a lot of folks out. What angle between -pi/2 and pi/2 has tangent of that angle equal to 0? Think about your unit circle. Somewhere between here and here, somewhere over here, between -pi/2 and pi/2, where is the tangent equal to 0? Remember, you can think of the tangent as being the slope of the ray coming from the center to the end of the unit circle. So it's right here at 0. The inverse tangent of 0 is 0. So this gives me -2 equals 1 plus c. All right, 20 times 0 is 0. So you subtract the 1 and you get -3 equals c. So f of x, the solution to the initial value problem, is e to the x plus 20 times the inverse tangent of x minus 3. This is the first kind of differential equation that everybody learns how to solve. Differential equations really are the language of science, the language of physics, the language of the physical and real world. It's all described in terms of differential equations. So even if you don't intend to study mathematics in particular, you just intend to study some sort of science or engineering or anything like that, solving initial value problems is going to be a big part. that is the end of today's lesson. On Monday of next week, I am going to show you how this whole antiderivative thing connects back to the area and distance stuff we were doing previously. It's quite beautiful, but you need to get good at this stuff before we can have a hope of getting good at that stuff. In particular, you need to really get comfortable with the definite integral notation. So please work hard on the homework that's out. If you need help with anything, come by office hours. I have an office hour today from 1 to 2 p.m. You can also send me a Canvas message to arrange meetings outside of that, or you can ask questions on the Discord. The Discord has thankfully been going really nicely, and I appreciate that that you guys have been talking to each other, and that's wonderful. Any burning questions before I let you go? Alrighty then, that's it. I will see you guys on Monday. Have a good weekend.